Here we go then, the last two lessons of new material before we get on to just doing a lot of practice. So really close to finishing the course here. We won't waste much time on this. This is one of those topics though, as per most of the transition metals topic you'll have seen by now, it's quite factual, isn't it? There's a lot of sort of little nuggets of information that you're expected to remember and be able to stitch together. I'd say here the big two things to be looking out for are colours and equations, and alongside that, stuff we've already dealt with, such as being able to draw these complex ions. There is a bit more theory as well, and it's the first thing we're going to do. So let's not waste any more time. We've got two lessons worth here. We're going to do it in two separate videos, and that'll be it. So first question for you to consider then, what do you think the pH of these metal ions is like? So let's talk about a hexaaqua complex of a metal. I'll give you an example. Let's take copper sulfate solution, that blue solution that you've been using throughout your school careers on and off. If I dip my pH probe or a bit of indicator paper into a solution of aqueous copper sulfate, where basically all the copper ions are copper 2 plus with 6 waters attached, so it's copper hexaaqua 2 plus. What do you think the pH would be like? Would it be neutral because it's a salt? Would it be acidic for any reason, or might it be alkaline for any reason? Just take a hunch. What do you think? And I'll tell you now. Actually, these aqueous metal ion solutions tend to have at least a little degree of acidity to them. Tend to be acidic. Those metal aqua complexes, we're going to have a look at some examples in a minute, can act as Lowry-Bronsted acids. So again, you know the definition for that. It means that they're a proton donor, H plus ion donor. So the solutions of those species have got H plus, or rather H3O plus, as we know that's what we really mean when we say acidic H plus, floating around free in solution. Let's have a look at a couple of diagrams to help with that. I won't keep saying this, but as is always the case, there will be times when you do need to pause the video, not just to answer my questions, but to catch up and take the notes. Take your time over this. As you know, these complex ions are, well, complex. They take a little while to draw. But how about you just stop, look, and read and listen for a couple of minutes before you catch up with the copying. Let's have a look at these structures here. On the left, you can see we've got a fully expanded, so a display formula, representation of copper 2 plus hexaaqua. So there it is, copper 6 waters, 2 plus charge overall. And look what's happening here. It's represented in the sort of way that we'd represent a weak acid. For example, that could have been ethanoic acid, reversible ethanoate. And I've shown the full acid-base interaction. So in other words, rather than just showing a H plus over here somewhere, I've shown the base, which in this case is water. We've got we've got water molecules. I was about to say we've got two types of water. Water is water. However, we've got water water molecules which are acting as ligands because they're coordinately bonded to the metal ion center. And then we've also got water, the solvent, in this aqueous solution. Either way, it's just H2O, but we've got two different sort of circumstances that these H2Os find themselves in. And you can see that proton transfer happens between a H2O ligand and a solvent water molecule. So when you look at the products there, you can see that the H2O has gained a H+, it's now H3O+. Oh look, and there it is. The hydrogen, one of the hydrogens off that top ligand, the way it's drawn here, is not there anymore. So simple enough then, we observe that these hexaaqua metal ion species, such as copper hexaaqua 2 here, can act as Lowry-Bronsted acids, and there's an indication of it being shown. Just to give you a bit of context and perspective as well, some of these hexaaqua complexes are actually really quite acidic. So the pKa for this copper hexaaqua complex, as far as I could find in the literature that I had access to, is about 4.5. So if you do 10 to the minus pKa, you get Ka. As you can see on the screen there, 3.16 times 10 to the minus 5 is what that would lead to. That's the sort of Ka value that we're often dealing with when we talk about weak organic acids. In fact, ethanoic acid, obviously a famous weak acid, with a 1 mole per dm cubed of it has a pH of about 2.5 or thereabouts. Its Ka value is 1.8 times 10 to the minus 5, and here we've got 3.16 times 10 to the minus 5, same sort of magnitude, similar pH per mole per dm cubed of unit in solution. So these are quite acidic, and this is just a metal 2 aqua. We'll get on to metal 3 in a minute, and we'll make a point about that as well. So just a few more things to say there. What we can see happening here is just straightforward Lowry-Bronsted type acid-base reaction. We've got proton transfer, in other words. As we've already made that distinction, a water molecule is a water molecule. However, here we've got water ligands and the solvent water, and the proton transfer happens from out of the complex to the surroundings, basically, but it's still just acid base. Now, you might be tempted to say, and I am tempted to say, that this H2O molecule at the top of the reactant on the left has acted as an acid. It hasn't really. Well, it's the one that's lost the H. However, it's not just that water that's been the acid. Remember that because of that coordinate bond there between the ligand and the metal ion center, really this whole hexaaqua complex as a unit is acting as an acid. And of course, it is the water molecules that have got the H's to be lost. But it's semantics. It's picking finer meanings out of words. But the way we say that, it's this whole metal ion complex that's been the acid, not just that water ligand. Maybe. Some people might disagree. In terms of what's happened, how we might describe it in terms of the ligands in this complex then, what we have not had happen here is ligand exchange. We haven't just seen a hydroxide come in and kick out a water. That's not what happened. What happened instead was a water ligand, an aqua ligand, became a hydroxy ligand by shedding one of its H pluses to a base, which was another water molecule. So it was a ligand change. However, it was a change in the ligands, but it wasn't a ligand transfer substitution reaction. It didn't involve the actual coming in and going out. It was just one turned into another. And of course, that must mean that the charge has changed. You can see on the diagram there, it goes from 2 plus to 1 plus. Despite the fact we haven't just added in a hydroxide, we have now got a water ligand minus a H plus, and so that's effectively OH minus. So yeah, the charge of the complex did drop by 1 unit. As always, again, the charge on either side of this is balanced. Now, again, take your time, pause the video as you need to. Take your time to look at this. You might not really need to be writing this slide down. You might not need to be copying all of that, but you need to think about it. So, what do you notice when you scrutinize those data? Pause the video, have a quick think, and then come back to me. I'm going to carry on straight away. Well, pKa really is the only difference, and therefore Ka. And you can see that the one on the bottom there, the iron hexaaqua, which is a 3 plus complex, notice, rather than copper's 2 plus, it's got a lower pKa, which means a bigger Ka, which means it's more acidic in solution. So the iron 3 hexaaqua is quite a bit more acidic than the than the copper 2 hexaaqua. I managed to draw these structures for myself in ChemSketch, but I was really limited on what data I could find for pKa and Ka values, suggesting that you don't need to worry about it in your exam. However, that's the point, is that once we've got these sort of results, we can compare them. Ideally, I'd have had an iron 2 and an iron 3 to make them a bit more directly comparable. Couldn't find the data, so be it. But this does match the sort of general trend that you need to be aware of on this course, which is that metal 3 aqua ions complexes tend to be more acidic than metal 2 aqua complexes. So they're both there represented acting as weak acids, giving a hydrogen from the ligand complex to a water molecule from the surroundings to form a hydroxy aqua complex with a one charge lower down, one less positive, and H plus. Of course, that H3O plus free in solution is what contributes to the pH of the solution. But yeah, so what you've hopefully spotted there is that the metal 3 one, the one at the bottom, is more acidic. That's an even stronger weak acid than ethanoic acid. So just again want to observe that these metal aqua complexes, they are quite acidic. Okay, fine. So there's that fact established and put on a bullet point for you to copy down then. Brilliant. The metal 3 aqua complexes are more acidic. You can see that I'm just using capital M as a placeholder there for whatever the metal might be. Why would that be though? So again, I want you to think for yourself a bit first before I give you the answers. So ideally what you'll be doing about now is pausing it again, having a quick think before you come back. Why is it that metal 3 might be more acidic than metal 2 hexaaqua complexes? Well, it must be to do with the strength of the OH bonds. We use a similar sort of argument when we're looking at why trifluoroethanoic acid is a stronger weak acid than ethanoic acid. And there we talk about F's, withdrawing electron density and polarization of the molecule and weaker bonds, OH bonds. Same story here, except we shouldn't be using the term electronegativity at all because it's a bit complicated here and we just don't want to go there. So instead what we will do, and this is what you need to do anyway, is talk about it in terms of the charge to size ratio. Now let's make the assumption, incorrectly, but close enough for what we're doing with it, let's make the assumption that the transition metal ions we might be interested in, so the 3D elements, let's imagine that their ionic radii are all the same. That's not true, okay? Let's just imagine they're all the same, they're similar. Simply because you're going from 2 to 3, that's obviously a 50% increase in charge. That's a big deal, having the bigger charge, even if the sizes aren't quite the same, and so it's not comparable. As you can see on the screen there, the metal 3 ions have got a greater charge to size ratio. There's more positive charge squeezed into a similar volume of ion. In fact, 3 pluses will be smaller than their 2 plus analogues, so ion 3 will be smaller than ion 2, as well as having a bigger charge. That leads to something that sounds quite a lot like the sort of descriptions we'd normally use when talking about electronegativity, but I don't want to use electronegativity at all in any of our descriptions here. So the metal 3 ions are going to be more effective at pulling electron density towards themselves. We've heard that sort of thing before in other contexts, such as when we looked at the perfect ionic model, which was in solid lattices, nothing to do with aqueous ions then. And so those water ligands have electron density withdrawn away from them more by a metal 3 ion than by a metal 2 ion. And so those OH bonds are effectively weakened. And so we say that the bonds are more labile. That's not a term I've put on the slide there. Labile means breakable, L-A-B-I-L-E, if you're really interested. But basically, they're weaker and more readily broken. So here we've got this iron 3 hexaaqua complex in the illustration at the bottom, acting as an acid when it gives a H to that water to make it H3O+. And we'd expect the position of this weak acid equilibrium to be further to the right than if that was Fe2+ in there instead. So a nice direct comparison there. So if I had iron 2 hexaaqua, the equilibrium would be further to the left than iron 3 hexaaqua. Here we've got iron 3 hexaaqua, so you can see once a H2O gives off one of its H pluses, leaving behind an OH minus ligand, then the charge of the complex goes down, because that's still iron 3, but this is now OH minus, so the overall charge has gone down. Hopefully that's clear enough. Hopefully that makes sense. Let's keep moving. Oh, sorry, just in case that illustration helps, I forgot that was there. So that arrow represents the idea of electron withdrawal away from the H2O ligands, and that would be happening all around the complex. I've just picked on this one. And so those OH bonds weaker, and so more readily broken, position of the equilibrium further to the right. There's always a bit more to it. You always have to consider enthalpy and entropy as well, but it's the entropy bit that we're totally ignoring there. Right, so we've now got a look at a variety of reactions that metal 2 aqua complexes do, and then next lesson we'll finish off by looking at those same reactions but with metal 3 complexes. There are a few little quirks and complications along the way, so we'll have to sort of get sidelined a couple of times to deal with them. We've only got 2 metal aqua complexes to deal with, copper and iron 2 hexaaqua. On the course, years ago, we used to have to do cobalt as well. Cobalt's really interesting. There's a lot of colour and a lot of interesting stuff, but it's not on the course anymore. So for this video, I'm very much sticking to what is on the course. There's a lot of very interesting chemistry which was cut out a couple of years ago. We're going to consider those 2 hexaaqua complexes, iron 2 and copper 2, reacting with those 3 bases, hydroxide, ammonia and carbonate. And some of it is very formulaic and therefore quite straightforward. Some of it isn't. Let's just get on and you'll see it for yourself. So things to think about, observations, so what colour things are and therefore what it would look like if you did it in a test tube. It would go from that colour to this colour and so forth, and writing equations. You've already got a flavour of what these complex ions are like in terms of their square brackets, lots of numbers and charges to keep track of. You've got to be really good at this because they're often usually only worth 1 mark. You've got to get it right. So there's our friend, the copper hexaaqua 2 complex. And hopefully you already knew that it is blue in solution because we're familiar with copper sulfate, which is aqueous when we're dealing with it in solution, and so there's an abundance of H2O ligands which complex with the copper. Sulfate doesn't form complexes with these metal ions, by the way. We're not going to even think about why. I wonder though, who's been paying enough attention. You do already know, or rather you've already been told this in one of these videos. What colour is iron 2 hexaaqua? You met it when we looked at redox titrations, where you'd be putting manganate in a burette and so forth. I wonder if anyone already knows. You should do. You'll need to. It's a light green complex in solution. So iron 2 hexaaqua pale green, copper 2 hexaaqua blue, and yeah, you do need to know these colours. AQA just call it green, but it is light green. So let's get on to the first of those 3 bases, which is hydroxide. Some common sense sort of thoughts that we better consider at first. What would our source of hydroxide be? So as you know, you can't just have a bottle of OH minus ions. There has to be a counter ion for it. I think we all know this one. Hopefully you're shouting it out. It's sodium hydroxide. It's by far the most commonly used hydroxide that we ever have in the lab. Potassium hydroxide is also around. It's got a bigger MR, so you don't get as much hydroxide per gram because the potassium ions are taking up a bit of the mass. But as we'll see in this as well, and as we already know, any alkaline solution has got hydroxide ions in it because alkali is hydroxide, aqueous, right? So it's not just something OH which will have hydroxide ions in it, anything alkaline will. This reaction then, this is the one between copper, hexaaqua and hydroxide, happens in 2 steps. So there you can see copper hexaaqua 2+, acting as an acid once, so it's donating 1 H+ to hydroxide, turning it into H2O. And the consequence there, as we saw on a slide earlier, is that one of those 6 H2O ligands, having just acted as a Lowry-Bronsted acid, is now an OH- ligand instead. So the overall charge of the complex goes down. It's still charged, therefore it's still soluble. That's a really important idea you'll hear me say multiple times in these 2 lessons. Therefore it's still aqueous. In the second acid-base step then, what we've just formed there, this penta-aqua hydroxy copper 2 complex, remember it is still copper 2, the oxidation state doesn't change any of this, it's just acid-base, it's not redox. That then acts as does another Lowry-Bronsted acid base reaction with hydroxide to form something which now doesn't have a charge. Come back to that in a second. You can see the state symbol. So yeah, another one of those 5 water ligands has given off a H to this hydroxide, the one that's coloured in white, to make a water. So now there are 2 hydroxy ligands, and there are only 4 water ligands or aqua ligands in the complex. So yeah, it's a solid now. Nice and handy for us, easy to keep track of. If the complex has got a charge, it's soluble, and this is all happening in test tubes in aqueous solution, so it'll be dissolved, it'll be aqueous. If it hasn't got a charge, it's not as polar by any means, and so it's not as attractive to the polar solvent water, and so it precipitates out. This copper bis hydroxy tetra aqua complex, the one that's bracket solid, that will still be polar, and so will still interact with polar molecules like water, and so will still dissolve a little bit, but not as much as when it's fully charged. All right. So basically, if it's got no charge, then we just assume it all precipitates. There will be a little bit soluble, but we'll see it precipitate. Let's just combine those 2 steps. This is what we're going to be doing every time after this slide. So we're never going to break it down into the individual acid-base steps. We're just going to say, look, basically, copper hexaaqua hydroxy, despite the fact that it's got 6 water ligands and therefore 12 acidic hydrogens in theory, let's imagine that each water can only act as 1 acid, so you've got like 6 H pluses to give off there. What we see is that these reactions stop. Once the substance precipitates out of solution, it is still there in the test tube having contact with the alkali, but basically the reaction stops. And so that's the limit. So therefore copper hexaaqua 2+ is a diprotic acid, a bit like H2SO4. It's got 2 H pluses to be given off, so it can neutralize 2 hydroxides to make 2 waters. And when that happens, it's down to its neutral species, which is where it stops as far as we're concerned. Moving on. Oh, sorry, I forgot. So blue solution. Anyone want to take a lucky guess then? I'm hoping that you're all talking out, shouting out as we go. What colour, what appearance might this copper hydroxide species here be? We could write that as Cu brackets OH2, but it is tetra aqua as well. Basically, what colour is it? Well, it's an easy one. It's blue. So far so simple. Copper hexaaqua is blue in solution. Copper hydroxide there is blue precipitate. Okay, fine. So there's a lot of blue for copper. Suits us. Now, a bit of a side note then, just a bit of a flashback to a previous lesson in the transition metals topic. Complexes like that one there exhibit cis-trans isomerism. The example we used when we looked at cis-trans isomerism in the transition metals topic was 4 ammonia molecules, sorry, 4 ammonia ligands and 2 water ligands, but anything where you've got this sort of 4-2 setup can exhibit cis-trans. So hopefully you can see the difference between those. We've got a hydroxy ligand at the top and one adjacent to it, and then alternatively we've got the hydroxy ligand at the top and one opposite it. So yeah, that's the sort of combination that we're looking at there. Which one's which? Hopefully you've already answered it. The one on the left there is the cis isomer. Okay, those being quite close together, those two that are the same. Trans would be the other one, they're like across from each other. Don't forget about that. Okay, we're on to our other metal 2 aqua ion, also reacting with hydroxide. It's pretty formulaic after you've seen the first example. So there's an equation exactly the same as what we had for copper, except with Cu scribbled out and Fe written in its place. So I won't labour this point too much, but as we saw before then, this hexaaqua complex has also given off 2 H pluses, one from each of 2 of its water ligands, to neutralise these 2 waters to make hydroxides to make 2 waters, leaving behind a neutrally charged complex. We could have just written Cu there instead of Fe, and it would have been what was on the previous the slide before last. What about the colours though? So we said that iron 2 hexaaqua is a green in solution. Sorry, green in solution. What colour might the iron tetrahydroxy tetraaqua bis hydroxy? What colour might the solid be? Well, here we go. I hope you're really excited to find out. Big reveal. If that's a light green solution, this precipitate is, well, it's that there. How would you describe that, I wonder? Well, what AQA expect you to call that is green precipitate. So, okay, then we'll do that. It's a pretty sort of grey-green, to be honest, when you see it in reality. But there you go. It's also, again, we just call it a green precipitate. That's all there is to say. Back in the olden days of A-level, we used to call this a gelatinous green precipitate because it was like jelly-like, definitely a solid. We don't anymore, but it's got a lot of water molecules as ligands, and therefore it can hydrogen bond with a lot of the solvent. It's a very sort of like gel-like substance. It's not like a powdery precipitate. It's very jelly because of all the hydrogen bonding that can happen between the solvent and the complex with all the OHs. Anyway, so a little further observation here. So something that we didn't have to say about copper. That iron 2 hydroxide species, the one that we've just labelled as a green precipitate, if you leave it in air for a while, so if you just leave it in a test tube, rack, come back to it 10 minutes later, that's what we call standing in air. There's air present and it's been there for a while. You get this orange or orange-brown observation. That is actually oxidation happening there. That's when our iron 2 hydroxide complex, which has got no charge, gets oxidized up to iron 3. Now, I am going to show you the redox half equations and therefore putting them together for this, but that's a bit of extra. However, those 2 half equations there are, as you should appreciate, totally manageable for you. I think first and foremost for this topic where we're talking about colours is just know the observation that if it's a green precipitate that goes rusty on standing in air, then it was iron 2, and green and that rusty precipitate would be iron 3 hydroxide. There's a difference in formula because iron 3 hydroxide would need 3 OH minuses to make it neutral, at which point it precipitates out. So something else must be going on here. Now that's all there is to say. I am going to say one bit extra before we move on to the next slide that you will also need to know all about. Let's just quickly combine those half equations, 4 electrons and 1 electron. So if I quadruple the iron 2, iron 3 half equation, first of all, you can see that I'm avoiding writing these complex species out. I'm just calling it Fe2 plus rather than Fe4 waters 2 hydroxides. Now I can rewrite that. This is a bit too complicated, I think, potentially for A level. It's always hard to tell where the end lies, but there it is written again with complexes rather than just Fe2 plus and Fe3 plus. Still got 4 iron 2s, still got 4 iron 3s, 1 oxygen, and so on. The waters and the hydroxides are the real pain here. That does balance, and that is correct. Basically, those 4 hydroxides that were produced are now in that complex because there were 4 of these that each got 1 more hydroxide. 2 waters were used up. 4 waters were kicked out because H2O4 4 times became H2O3 4 times. So 4 waters were kicked out, 2 were consumed. That left 2 on that side. Anyway, so that's the reaction that happens. It's oxidation. It's oxygen in the air, which acts as the oxidizing agent. Iron 2 gets oxidized up to iron 3, and we see that observation. Green precipitate goes orange or orange-brown or rusty on standing in air because of the change in metal species. We talked about colour in a previous transition metals topic, and we said that the factors that affect colour, it's anything that affects that delta E in the split d orbitals, and therefore the wavelength of light that's absorbed and the rest of it, and what we see is what wasn't. Here you've got a change in oxidation state and also a change in ligands because the numbers change. So definitely a reasonable chance that delta E and therefore the colour of it will change. Moving on now, this is all back to everything you need to know. There's very little extra on this that you don't need to know. Now onto our second base. So that was hydroxide dealt with for copper and iron 2 hexaquas. Now onto ammonia. What would our source of ammonia be? Now, I'm not trying to be funny here, but our source of ammonia is ammonia solution. The reason I feel it's necessary to say that is because ammonia, don't forget, as a pure substance, is a gas at room temperature with a low boiling point. So you don't have pure like gaseous NH3 when you're doing these experiments. It's going to be in a dropping bottle. It's going to be a bottle that looks a bit like that. And it's actually ammonia aqueous. So I just want to emphasize that, don't forget, ammonia is actually a gas at standard temperature and pressure. This is dissolved in water. And that takes me to another even more important point. Ammonia solution is alkaline because ammonia is a weak base. So ammonia being a weak base, it's going to act as a base then on water, which is amphoteric, as you always know. It's going to pick it off and leave behind a hydroxide, and that the hydrogen that got picked off is going to end up as a part of an ammonium molecule, sorry, an ammonium ion. So when we think about ammonia solution here, as well as the fact that there's NH3 present, which must be relevant, otherwise we wouldn't be looking at it. Also, there is hydroxide present. We've just done hydroxide. Hydroxide's also present in these species. Not concerned about the NH4 plus because it can't act as a ligand because there's no pairs of electrons that can form coordinate bonds with metal ion centers. And we ignore the fact that it's aqueous because all of this is aqueous in the first place. So, again, pause as always and carry on once you're ready if you need more time at any point. So first of all, we're going to have a look at copper hexaaqua 2 and ammonia. And first of all, within that, we have just an acid-base reaction happening. So that reaction there, yeah, it's not a typo. It does say hydroxide, even though we've moved on from hydroxide to ammonia. The first thing that always happens in our imaginations, and possibly in reality, is acid-base. So the hydroxide ions from the alkaline ammonia solution do what we saw them doing before when we had NaOH and form a precipitate. So the observations there, hopefully you know it's going to go from a blue solution to a blue precipitate. Try and remember these colours and follow with me as I go. Then after that, ligand exchange might happen. Now this is the thing, this one only comes up for copper, you don't see it for any of the others. You've met that species there before, the one that's got 4 ammonia ligands and 2 water ligands. You've met that before. It was the example that we used for cis-trans isomerism back in the transition metals topic. So we can write an equation, something like that. Now take your time to absorb that equation. I could have asked you to write it, but I thought we'll sort of jump into this one because there'll be more to follow. What's going on here then? So this is a formula of a species that you need to know. 4 ammonias, 2 waters. We said that was the limit of this copper ligand substitution with ammonia. It doesn't go up to hexaamine, it stops at 4 and 2 waters. So we're going to go from our copper hydroxy complex, the one that precipitated out as a light blue solid, and we're going to end up with this bis aqua tetraamine complex. And to balance it, I've got 4 ammonias coming in and basically 4 ligands popping out. And based on what we can see is left behind, both hydroxides and 2 waters must have left. So yeah, complicated, and these are the sorts of equations that we get used to writing in this topic. We also need to think about observations, remember? So I'm going to move on again. Now, we already talked about the fact that it's a blue solution giving a blue precipitate. And then that blue precipitate, if we continue adding ammonia, so drop by drop of ammonia solution, once you've already precipitated out that hydroxide, copper hydroxide, then the ammonia starts to get involved as the concentration of NH3 builds. It pushes an equilibrium to one end, and we start to see ligand exchange happen. What colour is that copper tetraamine bis aqua complex? I wonder if anyone's going to take a lucky guess. Well, obviously it's deep blue, no, it's deep blue. Okay, got a nice picture to show you on that now. Make sure you know the formula for that one, 2 waters, 4 ammonias. So here we've got a test tube where we've actually done that reaction. So what would have happened here? You might imagine a test tube that was first of all full of this kind of light blue solution you can see at the bottom. That would have been copper hexaaqua, basically probably copper sulfate. Then we added a few drops of concentrated ammonia solution, which is alkaline. And this solid mass of mush in the middle here is our copper 4 waters, 2 hydroxy ligands, no charge, light blue precipitate. And then as we continue to add ammonia, because then that solid barrier of copper solid had formed, copper hydroxide solid had formed, really the ammonia started to concentrate on the top. And once it's already got to the hydroxide precipitate, then the concentration really started going to push the equilibrium from that to this complex here. So that's the deep blue solution at the top. That's the pale blue solution of copper hexaaqua at the bottom. And in between, you've got copper hydroxide, which acts as a bit of a barrier once you've put a bit in, which is why you've got two kind of layers there. Anyway, so that's the colour we mean when we say it's deep blue. Notice because this species has a charge, we assume it's soluble. It is soluble. There it is in solution. It's aqueous. So charge, aqueous, no charge, solid precipitate. Let's do a similar thing for iron, hexaaqua 2+ now. So let's follow the same formula we had for copper then. First acid base. So same as what we had for NaOH being added. The alkaline hydroxide ions in ammonia solution lead to that. Followed by, and the observation there, light green solution gives light green precipitate again. Now, what happened next was a bit of ligand exchange. So following that pattern, oh, hang on, no, there isn't any. So the copper was a bit of a special case here, actually. And really, all ammonia does to iron 2 hexaaqua, and others that you'll see shortly as well, is just a bit of acid-base chemistry. When we get onto metal 3, we'll consider the fact that maybe rather than OH- for this one, you could have written NH3 there, acting as a base rather than as a ligand, a Larry Bronsted base rather than Lewis base then, and forming ammonium plus ions. We'll get to that when we look at the metal 3s, one thing at a time. So basically, yeah, the iron 2 hexaaqua and ammonia complex reaction is just what you saw for hydroxide, except you could have NH3 there as a base. As I said, we'll look at it in the metal 3 video. Last thing for this video then, and that is these metal 2 hexaaqua ions going with carbonate. Nice and simple, I'll be glad to reassure you here. So what happens? Well, where would we get our carbonate from? Probably the most famous carbonate at school is calcium carbonate, but not suitable here. Calcium carbonate's a solid, it's quite insoluble as well. It's not a very good way of getting aqueous carbonate ions into a system, i.e. into a test tube reaction. So we use a soluble carbonate. Fun fact, all group 1 salts are very soluble, so sodium carbonate is a good choice, and also it's very commonly available. It's made in massive ton quantities. Sodium carbonate's formula is Na2CO3. You'd be amazed how many year 13s just write NaCO3 and don't get the mark. That's something you should have been getting right since about year 8, although I appreciate that doesn't realistically happen. It's Na2CO3. It's one of the most commonly miswritten formulae in A-level chemistry, believe it or not, because Na1+ and carbonate 2-. So sodium carbonate's our source of carbonate, and when we put our hexaaqua and metal 2 ions together with some carbonate, we get a precipitate. So have a close look at that formula. You can see that we get an ionic substance, copper carbonate. Now, interestingly, it appears that the water ligands have been displaced. So not that we're going to dwell on it too much, but that would be a delta S positive change then, wouldn't it? Because you've got 2 particles turning into 7 particles. It's not chelate effect. It's not like EDTA kicking out monodentate ligands. It's just forming a big ionic lattice with positives and negative ions. But that's how we write it. I'm sure in truth, some of those coppers, some of those waters are still coordinated to the metal, and it'll be like kind of hydrated copper carbonate. I'm sure that's more realistic, but that's what the textbook says. We'll stick with it. Blue solution. So the observation here is going to be blue solution gives a precipitate, but what colour do you reckon copper carbonate precipitate is? Again, some of you might have met this back in lower school as malachite. Well, it's a blue-green precipitate. The malachite, if you ever used it in school, is like green, but the stuff you get here is sort of blue-green. It's probably as hydrated. So the observation, light blue solution to precipitate. You can tell that a precipitate's been formed in there because you can't see through it. And you can't see those watermarks that I haven't been able to remove. Iron 2 hexaaqua basically does the same thing, so nice and formulaic there. What colour did we say that iron 2 hexaaqua was? Pale green. Yeah, good, pale green. What colour do you think iron carbonate's going to be? So iron 2 hydroxide was green precipitate. Iron 2 carbonate is green precipitate. So it's blues and greens for coppers and iron 2s, which streamlines the whole effort. Hopefully you can see what's happening there. Now we could always write this as a complete equation, showing spectator ions. So let's imagine this was copper sulfate. There'd be an SO42 minus ion floating around. It was sodium carbonate. There'd be two Na pluses. There'd also be a spectator sodium sulfate. Irrelevant, which is why we're not showing it. But those ions must have a counter ion. Okay, so that takes. Oh, sorry. And there's the observation there. Now again, arguable. That's what we call a green precipitate of iron carbonate. That looks a bit more like the hydroxide. Actually, no, look at it again. Whatever you see when you actually do these or any videos that you watch, just call it a green precipitate. That brings us to the end. So let's just summarize what we've seen so far. I'll have a couple of paper handouts that match this kind of summary for you as well. So copper hexaaqua there in the box can be converted as such. You can add carbonate and it forms a carbonate precipitate. Obviously you need to be aware of all the states. That's for you to worry about. You add an alkaline solution, so NaOH or ammonia solution, and you get hydroxide precipitate. And then for copper 2+, if you add excess ammonia, then you get that hydroxide precipitate going back into solution, turns back into a charged species, so solid precipitate dissolves or redissolves to give a deep blue solution of that bis aqua tetraamine complex. Not quite as much to say for iron 2. It does the same thing with carbonate, does the same thing with an alkali, doesn't form any amine complexes that we're aware of, so that's that. In some of the literature, some of the textbooks, especially older ones, you might see the addition of chloride ions as well. Not officially on the course, however, we have looked at those. We just haven't learnt any colours of them. We looked at chloro complexes when we talked about changing coordination number, so watch out for that. But it's not examinable in the sense that you should know what colour FeCl4 2- is, so that's why we haven't looked at it. Okay, so you can see if you pause and have a quick look at that in your own time, that we've covered quite a lot of what there is to say already. The next and final video should be a bit shorter than this one. All we've got to do is look at metal 3 ions in solution. So basically we do the same as what we did for iron and copper here with iron 3 and aluminium. So join me for that, and then that's the end of the course.